Hello, good morning. Hello, good morning. I'm saying that twice because I think the live stream is beginning. I'm going to start hopefully in about 10 to 20 seconds, seeing chat messages saying hello, scrolling by. I'm going to post a quick note here saying live now. And I see the messages saying hello. Okay, I have like an itch right here. I think this is a new shirt. You might not have seen me wear this shirt before. I have this weird itch. Okay, I think it'll be fine. Welcome to another Coding Train. Today is Wednesday, January 16th. It's a bit of a strange day for a Coding Train episode, but it is the day that it is happening. And before I begin talking about what it is that I'm planning to code today, I just want to go over some plans that I have for this new year, that is 2019. So hello, welcome, Happy New Year. So I have some goals and desires and hopes and dreams and fears for this year. It's a little bit of a slow start. I had a wonderful time. Thank you to Le Tank Paris and Grow Paris for hosting me in Paris, France for a workshop last weekend. I really enjoyed that and getting to meet some of you, maybe some of you who are watching this live right now. If you were at the workshop in Paris, please say hello in the chat. So I was away for a while, I'm back, and then, oh, it's so exciting, tomorrow I leave for Los Angeles to attend Processing Community Day. So let me pull this up here. Processing Community Day, Los Angeles. So this is happening this Saturday. Maybe some of you who are watching this right now will be in attendance and I will get to see you. I will be there with my stickers. I would love to say hello to as many of you as possible. So please, I think there's still tickets available if you're in the Los Angeles area. But I'll also note that in addition to Processing Community Day Los Angeles, there is Processing Community Day worldwide. And so here we can see a map of all the different processing community days that are scheduled in the next month or so around the world. So I encourage you to find your local one and attend if you can and participate. I will also be at Processing Community Day New York, which I believe is February 9th, if I have that right. Just recently, I think if we go to twitter.com processing India, maybe? Is that the Twitter handle? Oh look, there I am. I won't be, unfortunately, at Processing Day in Bangalore. I think there are 3 Processing Community Days in India, but this particular one in Bangalore just released a, I don't know if actually, just has this little video of me saying hello Bangalore along with some other people doing that as well. All right, so I'm going to get my hair cut later today, so get used to this nice, longish hair and beard. It's time for Processing Community Day. I must get myself cleaned up to look like a professional person who knows what they're doing, which I am absolutely not. I banged on the desk, and the HDMI connection went a little haywire. Okay, now, I have some other things that I want to mention, but I'm going to, I'm still live streaming, aren't I? Okay, yes, so 2019, what is happening in 2019? Oh, so many things. So I will be continuing to make more videos about TensorFlow.js and ML5.js, which are both machine learning libraries in JavaScript. I will be coming back to that as time goes on. That won't be part of today. Things on the horizon are more Word2Vec, more I want to do Word2Vec, more Sketch RNN as in terms of different pre-trained models. I want to look at KNN, K nearest neighbor classification, and more. So those are things that are coming in terms of the machine learning stuff that I plan to do. I also, even though I've been saying this for the last 3 years, am working on updating the Nature of Code book to be written with JavaScript and P5.js, as well as some new material for that. So stay tuned to be on the lookout for that. Then, the other thing that I am doing, and I just put this together this morning. If I go to github.com/codingtrain, I forget what the repo is called already. I didn't put Intro to Data, APIs, and JavaScript. So I am planning a new playlist. I've made videos on this topic before, but they are somewhat out of date, and I think I want to take a new approach here. And the title for this playlist is called Working with Data and APIs in JavaScript. I'm repeating myself. This is a working document outlining future plans for our new Coding Train playlist, Working with Data and APIs in JavaScript. If I keep saying the name of the title, maybe I'll come up with what it is I'm actually going to do in this series. This course is for aspiring developers who want to learn about how to work with data in web applications. How do you find, collect, clean, analyze, and visualize data? I'll start with the basics of data formats, CSV, XML, and JSON. I'll then cover how to use promises and the JavaScript fetch function to load data asynchronously on a web page. I'll do case studies of several APIs and explain how to sign up and authenticate, make a request, and load the data. I'm reading this because I wrote this at one point, and I'm like reminding myself of it now. I'll look at how this works for both client-side and server-side. I'll demonstrate how to visualize the data using HTML5 Canvas and P5.js, and the course will end with a demonstration for how to analyze data using modern machine learning techniques such as classification, regression, and clustering. Wow, that is very ambitious. And then I have this like sample lesson idea. So this is something I'd like to do with planning, and I'd actually like to make examples in advance and have an outline and sort of a sense. And I'm hoping this will be like 10 to 15 videos. I know, so I see Simon Tiger, by the way, in the patron Slack channel saying, hang on. And I know exactly what he's going to write. He's going to say, you already have this playlist. I can say it before he types it. Of course, this is going to be a new reimagining of that content. I'm going to look at different APIs and new stuff and think about it because a lot of that stuff is out of date and things have changed. Okay, now what I want to just look really quickly, I just want to remember, I just have to look up something because I have to mention something, but I forgot exactly. I want to make sure I look at the guidelines. Okay. All right. Okay. All right, so why am I doing this? Well, I'm doing this for a number of reasons. I think this is an interesting and useful topic, but I'm also doing this through a learning incentive grant from YouTube itself. So thank you to YouTube and Google for supporting this project. I will be, my plan is to start these videos maybe at the end of January, beginning of February. So I'm asking you, the community, to help me organize the content for this. So you can file issues here, you can make pull requests. There's very little here. I'm gonna start building out an outline and making a plan for this, and all the code examples will also end up in theory in this repository as well. So this is something I'd like to do more planning for, and it'll be a little less of the usual sort of like live coding, I can't figure anything out shtick. And so I'm looking for your ideas and suggestions there. Okay. I wanted to mention that. That's the main thing. So Coding Train will be coming to you. I don't know, I'm going to try to have a regular, especially for this, what's essentially like a new course that I'm going to try to teach using YouTube videos. My goal is to have a dedicated weekly time that I'm presenting on this. And I haven't figured out what that time will be, but I can tell you that after today, the next live stream will be Friday, I believe that's January 25th. Yes, so I'm live streaming today, and then next Friday, January 25th, and then the semester at New York University ITP Tisch School of the Arts begins, and I will establish a weekly time. Okay. Okay, now, this brings me to today. If I can get through today, if I can make what I want to make today in the next 2 hours, I will be a happy camper, and I will ride off into the sunset, which is more like an airplane to Los Angeles for Processing Community Day, feeling fulfilled, satisfied, but more likely everything will go wrong. I will have lots of problems. I will fail, and you will learn something possibly from watching that happen. Now, what is it that I'm going to do? What I am going to do is not a new idea. And it is an idea that I've had in the back of my mind for quite some time. And it recently came to the forefront of my mind again when Smarter Every Day released the video Fourier series Smarter Every Day. So let me bring that up. So I'm not going to click on this, but this is what is a Fourier series explained by drawing circles, Smarter Every Day. So I went and made a coding challenge, which is this coding challenge. Subham in the chat is asking, how are you back in your studio? Weren't you in Bangalore like 2 hours ago? So there's this thing called the internet and video. I was not in Bangalore. I just said hello Bangalore from a video taken on this particular laptop with this particular webcam from New York City. I wish I had been in Bangalore. So this is the Fourier series, which takes a square wave pattern, breaks it down. What does it? It uses a Fourier series to visualize that, to add a bunch of different wave patterns together at various frequencies and amplitudes, and and to reconstruct the square wave. So that's what I did before. Now, if you watch the whole Smarter Everyday video, which is here, you will see that towards the end, I should be able to find this. Bill, where's that Turkish? Actually, I have all these in my, hold on. Just want to get all the links I need. This should be here. This is my, here we, no. Is this it? Yes, sorry. I was trying to find, so this is the article about the Fourier series from this Turkish website, which I learned recently translates to "Science is awesome," which I love. I think maybe there might be some more nuance to what the actual translation is, but that's the gist of it. And I don't know if this, I can't recall if this article gets to it, but by the end, it doesn't actually, but as part of the Smarter Everyday video, the researcher Doga used a Fourier transform, which is a way of taking a particular signal, a pattern, and breaking it into its frequency components to render the Smarter Everyday logo. And this is something that's been done many times by many YouTubers more interesting and smarter and clever than I am, such as Mathologger, Fourier. So there's this particular Epicycles Fourier series and Homer's Orbit. I highly recommend this particular video, and this particular YouTube channel is fantastic. Then there is also, what is the one that was, it's like, it has like a golden in it or something. What's the other YouTube video that, let's see, Fourier Transform YouTube drawing. I don't know why I'm thinking the word gold is in there somewhere. I don't think it is. There's a YouTuber. Someone's going to tell me. Hold on, let me get to the Slack channel. Gold-plated goof. Okay, thank you. I knew I watched something like a month ago. There is also, there it is. Oh, look at this, gold-plated goof. Fourier analysis for the rest of us. So I am going to, let's pull this up. Hi everyone. Okay. Let's okay, here. Let's put this here. Let's get this over here. Let's get that Mathologger.
So now we're ready to reveal the inner work.
There we go. Let's get this here. Okay, so these are, and then of course, it goes without saying, there is what is like, for me, the sort of canonical explanation of what is a Fourier transform, the three blue, one brown video, but what is the Fourier transform, a visual introduction. So this is all of my background, and actually on the flight back from France, I worked out my own version of this in a slightly more simplistic way, which used a basically one-dimensional Fourier transform to process the x's and the y's of a path separately and visualize those x's and y's as a series of circular epicycles and to render this particular drawing. And this particular drawing is the Coding Train logo transformed into a continuous path, which came via Tom Fourier, who I met in Paris. So this is exactly what I want to build today on the Coding Train. So I want to do it this way first, separating out the x's and y's separately. And then I will revisit it, I think, to do it with them together. This has to do with the way the sort of complex numbers work. And my plan for today is to really like hand wave all of the math. I mean, I'm going to implement all the math in the code, but the explanations for why the math works that way and deriving the math and gaining an intuition of the math, I'm going to refer to those 3 videos, 3 Blue, 1 Brown, Mathalogger, and Gold-Plated Goof as reference points. And I will just simply implement this, basically like write the code for this exact equation here, which is the discrete Fourier transform, in JavaScript. So that's what I'm going to do. So, and I think that I will begin with this as my code base. I think I want to simplify it. I'm trying to decide whether it makes sense for me to start over. The thing is, I'm going to use exactly this. So I think it makes sense for me to build off of it rather than start over from scratch. I'm trying to think about this. I'm also trying to decide whether I should do a separate video that just writes this equation into a JavaScript function, and then I'm always struggling with this multi-part single. You know what I'm going to do? Here's what I'm going to do. I can never figure out what to do to make multi-part, single part, so I'm just going to do it. This is a live stream. Here we are. I'm going to live stream it. I'm going to do it in the order that I would do it if I were just on the plane trying to figure this out, building off of the previous coding challenge that I had. Then when we get to the end, I will reconsider whether any of that, how that might necessitate breaking up, and then I can obviously do some intro or outro explanations that Mathieu can put together later. So as you are watching this today, please help me keep track of like how long it's been for the actual substantive content, and whether it makes sense. You like sort of note as you imagine the sort of edited version of this coming out later as a coding challenge, if you imagine it being broken into separate parts. All right. Any questions or comments before I begin? I'm happy with this being like a final edited version of this being an hour, because this is a complex enough thing to work all the way out. But I don't want, my goal is for the coding challenge videos to not be longer than an hour. And the sweet spot is somewhere between 20 and 40 minutes. Okay. C. Benedict Busol, please check this out, fourier-series.surge.sh. Well, that sounds like a reasonable URL that I can type in without. Oh, cool. Oh, you know what I should do before I forgot. Before I do any of this, let me go to thecodingtrain.com and go to coding challenges. And let's look at, I think I might have already, did I already do this? Let's look at some of these community contributions. I sort of have a memory of clicking through some of these already, but let's do that. So let's show, by the way, so if you weren't aware, every coding challenge video has a corresponding web page on thecodingtrain.com, and there is a process by which you can add your own version. Oh, looks like there's a little typo here which could get fixed, and a little link about how to do that. Requires some knowledge of how Git and GitHub works, but we're here to help. There are wonderful volunteers who help to maintain this website. Thank you so much to those people. Gruselhaus most recently has been really doing a wonderful job of merging and tracking all of these contributions. So let's look at some of these. And so I'm sorry I'm not I guess let's do them one at a time. So let's look at the square and soft tooth wave with sliders by Lottie Bonnet. So if we look at this one, okay, so we can see this is cool. So this is nice because it lets you like change which wave you want, change the speed, the number of iterations of the Fourier series, and the radius. That is wild. So this is fun. So a lot more interactive features than I had. Let's look at, now it's sound. Oh, cool. All right, I don't know what's going on here. Square wave. Whoa, volume control. I don't hear any sound. I don't know. Oh, it's actually playing the sound of the wave pattern. This is wild. This is so cool. Great work, Stellar Tux. Okay, Rainbow Fourier series. Juan Carlos Ponce Campun. Oh, look at that. That is beautiful. Ooh, look at all these little sliders. Oh, I can actually individually control the various epicycles. That is crazy. That is fun. Let's look at Fourier Transform processing class. So unfortunately, this is great to see. I'm not going to run this right now, but you can see if you're looking for a processing port. There you go. Square wave Fourier Transform animation. Uh-oh. I'm not pronouncing Mathologer correctly. Mathologer? I better get that right before I start before I officially reference it. Okay, this is lovely. Convergence animation of square tooth Fourier series. Lovely. And then, did I click on this one? I'm sorry, I'm confused. Yes. Oh, look at this. Wow. Okay, this is crazy, by the way, because look at this. I guess I can write the formula in here, and it'll be live interpreted. Submit. Yeah, that's crazy. And I can do the number of terms. I can do a custom wave, a triangle wave, line. Oh, I can pick colors. This is fantastic. So you can see, look at all of these amazing variations on the Fourier series video. All right, watch the okay, hold on. Let's see. Somebody in the let's figure out the correct pronunciation of Matholog. I'm just going to watch it over here on my invisible computer. So you can see, look at all of these amazing whoops. Variations. Unfortunately. Fourier series video. All right. Hold on.
Okay. So to start off, I've got four images for you.
Oh, by the way, the thing that I ended up clicking on is this awesome times tables video. All right, wait. I need to figure out how to pronounce this. There must be, what's a video that I can watch where the channel name is pronounced?
All right, so the other day I sat with my
kids. This is not working very well. Fourier, epicycles, is it in this video?
Who's Limit Moon? Welcome to another Mathologer video.
Mathologer. Welcome to another. This is not a Mathologer video, but that was a Mathologer video. Mathologer. All right. I think I will begin. is also useful. I think I already referenced this one though, so here's another one. And this is, by the way, this is also an excellent reference, which I will refer to in a second. Okay. All right. Mathologer. Let's cycle the cameras. Let me make sure I have a whiteboard camera working. Nope. Wait, why is it? That is weird. What is going on? That is the weirdest thing. Hold on. The whiteboard scene is like, for some reason, there we go. Okay, that's a slightly better sign that it's now a black. You would think that I would check these things before I begin, but if you've watched the coding train long enough, shoot. Okay, so hold on. This, unfortunately, you're seeing, I know you're seeing a blank black, but I'm gonna hope, there we go. Loose cable. Hello. This is working now. And, look at the terrible glare. Where's that glare coming from? Is it this light? Yes. So I guess I have to point that more like over there. And then is this marker a reasonable marker? I'm going to draw off of your view just to sort of see. No, it's not. It's a terrible marker. I have a bin of markers here. Let's find one. This is a beautiful marker. I should be able to switch now back and forth. Yep. And by the way, if you recall my holiday special, I still have this ukulele, but it's not tuned. Should I tune it real quick? Because maybe somebody will like to write me a Fourier Transform song to the tune of something with easy ukulele chords. I better not waste time doing this right now. Come back to that if necessary. Julius asks, why don't you make video games anymore? So this is my plan for the spring. This is what I'm hoping to do in 2019. My goal is to have these sort of like planned sessions to do this new playlist about data and APIs. And then other days do more of these kind of goofy coding challenges, some of which things like make a Rubik's Cube, make Tetris, these things that get requested a lot that I would like to try to do. So we'll see. So you might be in for some weeks where I have 2 live streams in 1 week. All right. I am now ready to begin. Okay. That's the sound of me blowing my nose. Okay. So let me just get one more. I would like to go through some of the community contributions for some of these other more recent coding challenges, but I'm going to hold off on that. Okay. What is this? What am I calling this? Fourier Transform drawing? I guess I could call this like discrete Fourier Transform, epicycle drawing something or other. Okay. I'm stalling. Just check my email, check my Twitter. No, I'm just kidding. Here we go. Let's do it. Let's go. Like Voyager, Mathologer. Need a checklist. Oh. Ooh, Alka is suggesting the checklist. When did that suggestion come in? Just a couple minutes ago. That's a thing from CJ and the Coding Garden. I'll think about that for next time. I'm going to go back to my just winging it thing. Okay, here we go. Hello, welcome to Coding Challenge, Discrete Fourier Transform to somehow make this. So I was recently on an airplane and I had quite a bit of time and I made this. And this is, what this is doing here is it is taking this path, this Coding Train logo, thank you to Tom Fourier who provided this Coding Train logo as a continuous path, and taking the two signals of that path, all of the x's is really like a signal, all of the y's is like a signal, and using something called a Fourier transform to take that signal and break it down into a bunch of wave patterns. And then those wave patterns are visualized with a sequence of rotating circles, and then that is ultimately the end point of those rotating circles, sometimes referred to as like epicycles, is used to draw the path, the x's and the y's of this particular logo. Ah, boy, I don't know if I was able to get through explaining what's going on here, but this is what I'm going to build in this 7-hour and 32-minute video. I don't know how long it's going to be, but it's going to be quite long because there's a lot of components down this. Now, the good news is that I have somewhere to start from. So if you've watched some of my videos before, you may remember me from Coding Challenge number 125, Fourier series. This looks quite similar. This was a coding challenge where I used a Fourier series, a sort of predefined mathematical series of wave patterns when summed together to get a square wave. So while this is like a sort of like known famous Fourier series, what I'm going to do, which is different. So let me bring over the whiteboard. Let me talk about this. Okay, so the idea of a Fourier series is, okay, let's take all of these wave patterns of various frequencies and amplitudes, add them together, and I'm not saying these actually add together to that pattern, but to converge to like the square wave. This is what's known as a Fourier series. In this video, what I want to do is instead a Fourier transform. I want to go in the other direction. I happen to have some arbitrary signal, which can be expressed as a wave pattern, and I want to be able to take this and subdivide it into, basically transform it to a bunch of different wave patterns with varying frequencies, amplitudes, and there's something called a phase here, which is going to be important. It's sort of like the offset of where the wave pattern starts. If you're like, what are you even talking about? What I would suggest is pause this video right now and look in the description. So there's tons of resources on this. All over the world and internet, but there's 3 particular videos that I have watched in the last few months when thinking about this that I'm going to refer you to right now. One is this 3 blue, 1 brown video. Oh, I'm sorry. Sorry about that. I don't know. I didn't really like this explanation, but here. One is this 3 blue, 1 brown video, but what is the Fourier transform? This video will look at and give you a kind of animated visual sense of what's actually happening in a Fourier transform, which, by the way, well, I'm going to come back to what I was about to say with by the way in a second. Then, because it is a reason why I'm having kind of trouble explaining this is something I want to just mention. But hold that thought. Me, you, or keep watching, or not, whatever. I don't know what to do. There's also this particular video by Gold Plated Goof, which does exactly the same thing. by the end of the video, renders a path through a set of circular epicycles. Fourier analysis for the rest of us. This is if you really want to dive more deeply into the mathematics behind a Fourier transform. This video I would suggest, as well as the Mythologer video, Epicycles, Complex Fourier Series, and Homer's Orbit, which basically is another video on exactly this topic. The difference between those videos and what I'm going to do here is I'm going to sit here and code every single bit of it step by step by step, but I'm not going to, and I'm just going to look up like, okay, what's the equation? And then I'm going to rewrite that equation in JavaScript, but I'm not going to derive or prove or really go deep into these equations. And for that, I would suggest checking out these other background videos. Now, I'm going to get started coding in a second. One thing that I want to mention here, and the reason why I was having trouble here is what you'll typically, where you might have typically heard the word Fourier transform, at least in my world, the world of kind of like new media arts and computational things, you might have seen, and you'll even see this in like the P5 library as FFT. We'll see this over and over again. FFT stands for fast Fourier transform. So this is a video where I'm actually going to write the Fourier transform algorithm. I'm just not going to bother to write one that's fast. I don't care about it being fast because I don't need it to be fast. But Fourier transforms are so useful and important in so many fields and applications that being able to have an algorithm that runs super fast to do a Fourier transform is incredibly useful. And where you would have seen this and seen FFT is in the context of digital audio signal processing. Meaning, if this would have been easier for me to explain. The drawing thing is kind of weird, and we'll see that this things might come full circle for you by the end of this video in the way that they have for me in the last month or so of thinking about this. But typically, if this were a sound wave of like me talking, what you might want to do if you are an audio person is take that sound wave and break it into parts. What are the amplitudes of different frequencies that make up that sound wave? You can use this to reduce noise, to do some kind of processing, to create an audio visualization. And the P5 FFT function basically connects to a sound file or a microphone input and gives you a big array with the amplitude of the sound at various different frequencies. So you can do things like draw one of those, 80s style graphic equalizers where you see all the bars kind of bouncing up and down as a piece of music is playing. So this is the background for all of this. And so now is the moment for me to start coding. What if I take any arbitrary signal, the steps are take any arbitrary signal, I'm going to make one up, or it's going to be the path of the coding train logo. I'm going to write the discrete Fourier transform algorithm, which I'll find on the Wikipedia page, which is a slower version of ultimately like other implementations of the algorithm like fast Fourier transform. Then I'm going to take the results of that and turn it into a sequence of rotating circles at various frequencies with various amplitudes at various phases. And then I am going to see if that redraws the logo. And now that I've already made like 30 minutes into this video, I'm going to begin. Time out for a second. Oh, it checked. So I don't know. How long, if you had to estimate, anybody paying attention, like how long was that explanation of like even just like where I am? Anybody have a guess? Like does that, like that explanation, I mean, I wonder if I should do it again and try to make it shorter. Because that was kind of long. I'm gonna wait for your feedback and I'm gonna erase all this. That was like my rehearsal. What time is it? 11:15. Also have to keep going here. So I don't want to be here. About 6.5 minutes. That's not terrible. I'm seeing 10 minutes too long, 20 minutes, 8 minutes, 35 minutes, 3 minutes, 5 to 8 minutes. I trust Alka and the 6.5 minutes. I'm going to start coding 7 minutes, and I guess I could come back and redo that later. Also, there's always like little things to trim out that Mathieu is good at figuring out, so it might be a little bit less. Okay. So what did I reference? I referenced this. Oh, I didn't reference this, but that's fine. Oh, I didn't reference this yet. This I need. This I'm going to need also. Okay. Yeah, just people don't want me to. I have to realize I'm doing. If I were not live streaming, I would do that again. But since I'm live streaming, I'm going to keep going. Okay. Okay. I'm just sorry. I'm thinking to myself here. So actually, give me a second, because what I want to do is I don't want this slider in here. I'm going to start with this, but I want it to be a little bit simpler. Where is it using the slider value? Let's just change this to like 5. Okay, that's fine. What? Oh, let's go to create slider. Okay, so, okay, and okay, and let me create a JavaScript file where I'll write the Fourier function. So this is, let me make sure I have my reference open here. So again, unlike some coding challenges where I really do completely just make it up from scratch, I'm not gonna like read my code and retype it. I'm gonna try to figure it out as I go. But in case you wanna like follow along a little bit more in advance, or like be able to catch the mistakes I make more quickly, this is a good reference point. So this is my, what I did on the plane. This is my implementation of the of that Fourier Transform algorithm. And then, and I just want to like peek at these for a second. And then assuming that I have some set of x's and y's, I call the function and then loop through it, and the angle, the amplitude is the amplitude, the angle is the phase, plus time times frequency, and time always goes up by 2 pi divided by how many things I have. Okay, that may all make sense. I will explain that as I go. Okay. Okay. All right, let's cycle the cameras. I will consider at the end coming back and redoing the intro to this, but I'm not going to worry about that right now. It's also possible that I would make implement the discrete Fourier transform algorithm as a separate video, but I think, okay. I am ready to start coding, finally. Now, this is where I left off before in my Fourier series coding challenge. And the difference now is what I want to do is be able to have an arbitrary signal and then compute what all of these amplitudes and frequencies and phases should be. So the way that I'm going to do that is, so let's think about this. This is really like all of a bunch of y values that I'm calculating. So let's make an array called something like y. And this is going to be the signal. This is my signal. This could be audio, it could be y positions, any arbitrary digital signal / array of numbers. Then what I want to do is I want to have the Fourier transform of that particular signal. So I want to say Fourier y equals Fourier transform, or maybe DFT, discrete Fourier transform of the y value. So this is the idea. The first thing that I need to do is compute the discrete Fourier transform of an arbitrary signal. Now I need some kind of signal. So I think what I'm going to absurdly do is hard code the signal. Let's actually make it the square wave, and then we'll know if it kind of worked. So what is the square wave? Square wave would be something like 100, 100, 100, negative 100, negative 100, negative 100, and then do that a few times. All right, so so this is going to be my arbitrary signal, which I'm just hard coding the square wave. And then we'll do some interesting things that maybe I'll try a Perlin noise signal or just a sine wave signal. We'll try different things, random numbers, see what that does. So then this actual code here can largely stay the same, because in theory the difference is now, instead of following the specific Fourier series for the square wave, I just need to take the results of my discrete Fourier transform. So this would be a loop that's going to go through the length of that transform. How many different wave patterns are there that I'm adding together? And then this ultimately I'm going to have to figure out. So let's comment this out right now. And there's a little bit of an issue where I have this x and y as local variables here. But I think this will be okay. So let's refresh this, and DFT is not defined. Okay, step one, let's write the discrete Fourier transform algorithm. Now pause for a second. There's a small chance that what I'll do is have that be a separate video and then just have it appear, but I'm going to try writing it right now within this video. Okay. So I'm going to start by making a function called DFT. It's going to have some array of values. And now I need to, at the end, I need to return something. The idea is that I'm going to return the discrete Fourier transform of those values. What do I do? Well, guess what? The way that so a couple things. One is I highly recommend if you want to pause this video right now and read this particular article on the Algorithm Archive by James Schloss, or the LeoIOS YouTube channel. This is a really nice article about Fourier transforms and the discrete Fourier transform algorithm, and this particular algorithm for FFT. But what I'm going to do is I'm just going to follow exactly what's here on the Wikipedia page. So my signal is x sub n, lowercase x n. So what I need to do is basically, and the transform is capital X sub k. So I need to write a function that computes this exact equation and returns it as an array. And this is exactly what I'm going to do. This is exciting. Now, one thing I should mention is that in order to work with Fourier transforms, I need to understand something called a complex number. Now, if I recall correctly, the last time a complex number came up on this YouTube channel was probably in my Mandelbrot set coding challenge, where I visualized the famous Mandelbrot fractal, and I referenced something called an imaginary number, and I was way too informal and loosey-goosey and jokey about how I talked about imaginary numbers being this pretend thing that doesn't exist, which is absolutely incorrect. The reason why the term imaginary is used is because there is no real number solution to the square root of -1. But the square root of -1 is referred to in mathematics as I, I is a complex number. A complex number is a number with both a real, A, plus an imaginary component. So it's two real values, a real value and another real value kind of multiplied by I, the square root of -1. So this is the idea of a complex number. And by the way, another way for me to refer to a complex number is by its position on the complex plane. So if this were the real axis and this were the imaginary axis, this would be A and this would be B, and this is a vector representation, whoa, of this particular complex number. So why do I bring this up? The reason why I bring this up is that the Fourier transform algorithm, even if I start with an array of real numbers, single numbers, I'm going to apply the Fourier transform and get out a complex number. What I'm going to return from that function is both A's and B's, otherwise known as the real component, which is often written in code as like RE, and the imaginary component, which is often written as IM. So this is one bit that I really need to understand before working with this formula. So now that I'm looking with this formula, so by the way, before I move on, did I say anything like wildly incorrect there about imaginary numbers and complex numbers? Am I going to mention Euler's formula? I probably should. Yeah, I wasn't going to. So, I mean, it's an important, so I should mention it because this is what follows via Euler's formula. And Euler is the correct pronunciation of that, right? Not Euler, as one might think. Yeah, Simon, that's a very good point. Simon says a real number is actually a complex number with an imaginary component of 0, which totally makes sense. Yeah. Okay. I thought you weren't going to go into the math. Right. I just need somebody to tell me that Euler, that Euler, I'm pronouncing Euler correctly. Euler. Okay, great. Two more things about the math that I want to say about this particular discrete Fourier transform. Number one is the top line there is the actual formula for a Fourier transform. But there is something very well known and famous in mathematics called Euler's formula, which allows us to take that top line and turn it into what is here. And this is going to be much easier for me to actually implement in code. So I'm going to take this second line here, and that's what I'm going to implement in code. So that's kind of the most important thing. Now, the other thing we'll see, and I feel like I should, let me take a second here, actually. So let me go back. What I want to do is, hold on, sorry. I'm thinking here. I kind of feel like I want to write that formula out so I can, yeah. So ignore that thing that I just did, Mathieu. Great. All right, let's take a quick minute to rewrite this formula on the board so we have it for reference. Oh, shoot. I need to have it for, okay, hold on. I think I can see it. You'll all help me. So Mathieu, this could be like sped up or something when we make the edited version of me rewriting the formula, because I'm literally just going to rewrite it. The question is where? Actually, you know what? I'm going to erase this. Because this I kind of want to keep later. This will be important. So let's rewrite the formula. N equals 0 to capital N minus 1. X sub n dot cosine of 2 pi k n divided by n. Shoot, I'm going to run out of space. I might have to do this again. Minus, I'm totally going to run out of space. I'm such a jerk. Sorry, everybody. Write this again. N equals 0 to n minus 1 of x sub n not cosine of 2 pi k n n minus I times sine of 2 pi k times n. These are the same thing, by the way, so it's sort of a little bit silly, but that will help us. Okay. Okay, great. Did I get that all? Awesome. Okay, great. So I have the formula there now. What was I saying? Ah, yeah. I definitely don't know the formula by heart. Okay. I should mention Euler's formula. Okay. All right. So now is this moment that happens to you in life, where you see one of these formulas on a Wikipedia page or in a math textbook, and you're a creative coder making some kind of visualization thing, and you just want to stop. But together, you and me, we're not going to stop. We're going to figure out how to translate all of this notation and symbols and stuff into JavaScript code. Now again, it'll be super interesting to go down the rabbit hole of like deriving all these formulas and the background for how Fourier Transform works, but I'm not going to do that. If you look in the video's description, there are several excellent videos and resources linked to that will give you that background. But I do want to mention one thing which is quite important, which is that this particular formula on the top here for the discrete Fourier transform uses this symbol E, Euler's number, or the base of natural log. This is a very famous number in mathematics, much like pi. But there's also a very well-known formula called Euler's formula, which looks like this. E to the I, which is the complex number I, x equals cosine of x plus I times sine of x. Really interesting. Kind of looks like polar to Cartesian coordinate transformation. All this stuff is interrelated, right? But so that is where, if I come back to here, this is where we get the, this is where we get the second line here using Euler's formula from the particular formula that's up top. But this is the one that I want to implement, and I have written the formula out right over here so we can unpack it a little bit. What are the components we need to understand? Now really, if this were a math lesson about Fourier transform, we wouldn't be using summation, we would be using integration. But because we're working on a computer and I need to write a loop and I don't have infinity as a tool that I could just use, I need to, instead of doing integration, do summation. And that's why also this is called discrete Fourier transform, because I'm doing it over this sort of like discrete space. Okay, so this means summation. So this should give you a clue that I can just do like a for loop, going from 0 all the way up to n. And by the way, n is going to be the length, the number of values I have in my signal, so the length of that original array. And that's kind of, oh, and then the other thing that's really important is that basically what I get to do is separate out, this is the real component, and this is the imaginary component. So even though this is all written as one formula, I'm going to sum up all the real components and all the imaginary components together. And by the way, as Simon, who has been watching this live, pointed out to me, there are only complex numbers. The term imaginary is really too bad that it's called imaginary because it's very misleading. But a real number is just a complex number with the imaginary component as 0. Okay, so I should be able to start writing the code for this now, right? This is my signal. It's a little confusing that this is called x because I called it y, but this is just the values, the vals. This n is vals.length in my code, and then k, we're going to have to work out what k is. I know what cosine is, 2 pi, and all these things. So we're going to work out what k is, okay? All right, so what I'm going to do is, let's create a variable called Fourier. Then let's say n is vals.length. So I'm going to, and let's do n, let's follow this. N goes from 0, I forgot something first of all, I'm in the wrong, good thing I'm in the wrong screen. I know that, everybody. Sorry. K is a constant. I got it. I totally screwed this up because I forgot something super important. Oh boy, I'm so silly. What is K? This is I completely forgot to write what is quite possibly the most important part of this formula over here, which is capital X, big X, sub K equals. So this is what I'm trying to calculate. I'm trying to create an array of K elements. And each element K, I'm going to sum up n from 0 to the n. So there's like a little bit of a nested loop going on here. I want to loop through every K, which is going from 0 all the way up to n, and then also sum up. So K is going to stay constant within each one of these. And K is actually really the frequency. We'll see that. The frequency of the particular wave pattern in that slot. Okay, so let me come back here. Now, let me start to write the code for this. So the first thing that I want to do, so I have, sorry. Okay. All right, so let me write the code for this. The first thing that I want to do is create an empty array. This is where I'm going to store all of the results. Then I need to write a loop, which is let k equal 0, k is less than n, k plus plus, and then I'm going to be saying Fourier k equals something. So this, by the way, I mean, I could call this like capital X if I wanted to be, and maybe I will, just to like follow this notation exactly. So this is capital X, this is lowercase x. So let's actually, as silly as this might be, let's change this to x so I can use all the same notation as that formula. So I'm trying to calculate this. Now in order to do this, I need to, for each one, go through n. So this is where the nested loop comes in. To calculate each element of capital X, index k, I need to sum up n going from 0 to the n, okay? And then I'm going to start doing this formula. Okay, so I need to sum up what? I need to sum up both a imaginary real component and an imaginary component. So let's make a real component and an imaginary component. The real component is going to go up by some amount, and the imaginary component is, no, I do not want to ask Siri. Actually, Siri, please, could you help me with this Fourier transform problem? Just write the code for me. So I'm going to sum up the real and imaginary components. And then I'm going to make some object, which is basically just, and I know I could, what's that thing called where, but I'm not going to worry about it right now, the fancy ES6 way of making an object, if I'm doing this. So then I'm going to make an object that has the real and imaginary components, and I'm going to return it. Okay? There we go. So this is the process. Whew. I could use, Holobrine in the chat is saying use a p-vector. I could certainly use a vector object, but I'm going to write it this way. So, okay. So here we are. Good, 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 good. That's I've got this and this. Now I just need to add this stuff in there. So let's do the real component first. Now one thing you might notice, this appears twice. So if anything ever appears twice, that might give you a hint to just put that in a variable. So let's do that. So let's say, I don't know what to call that. I'm going to just call that something. Somebody give me an idea of what I call it. I'm going to say 2 pi times k times n divided by n, right? So this, I'll call this is like the, it's like the angle. I'll call it theta. I don't know, what should I call it? What should I call this? Somebody give me something to call this. I can't think of it myself. What's that called, though, in JavaScript where I see the answer now. Phi, angular speed, phi. Yeah, it's like the angular speed. Angle, I could call it angle. Yeah, call it phi or some angle name, yeah. All right, so the chat's telling me to call it like angle or some angle name, but actually phi is a good one. So because it's the value that's going into cosine and sine, which is like an angle, or a Greek letter phi is often used. So I'm going to call it phi, and then I'm going to say the real component equals, and I'm looking over there because that's where my formula is written, is going to say x index n times cosine of phi. Boy, this should look strangely like a lot of code that I write a lot. And then x index n times, and this should say cosine, times sine of phi. But one thing you'll notice here is that there is a minus here. This minus here is quite an important detail. So what I'm going to do is, I don't know the best way to handle this, but I could just say minus equals, but maybe let's say minus equals. Let's do that. Okay. And then this is called enhanced object literals. Thank you. I can just say this. So this will give me that and there. Okay. So all of that explanation. Wow. And here we are, discrete Fourier transform. Okay. I'm just taking a break for a second. I'm going to double check. Just out of curiosity, I'm going to double check this code. Yeah. Or remember to define n. Thank you. Also, one thing that I'm noticing in the example that I wrote, I did this. Why did I do this in the example that I wrote before today? Does that matter? I mean, it's like normalizing the vector. Does that actually matter? I'm not sure. Where did I get that from? I don't see it anywhere in here. Okay, I'm not going to worry about that right now. Yeah, this is going to be very important in a moment. But I'm not going to worry about that. Okay. Ethan Davidson, see you at PCD LA this weekend. Awesome. Okay. Why did I divide by? Oh, it's the average contribution at that frequency. But no, it's not normalizing it. That's just dividing by n. I'm not sure why I did that. It's phi, not phi. Mr. Zakrinkny is asking a good question. Yeah, I know I need to, okay. So I'm pretty sure it's phi. Yeah, all right, hold on, sorry. All right, so many things are coming at me all at once in the chat. So let me do a couple, let me reference a couple of those things. All right, so thank you to the chat for asking a couple key questions and for pointing out some errors. For example, I forgot to actually define what n is, which is x.length. You know, I should probably get in the habit of using the variable declaration const when I know it's something that's going to stay constant like this. So I will attempt to use that here. These cannot be const because I'm adding them up together. I also want to, there's a couple other pieces to this. Yes, sorry, Simon, yes, I see what Euler's formula is, thank you. Okay, hold on. Pronunciation is so. One noted that in the UK, two in the US think that phi is the preferred. Yeah, I think in Greek, so I'm pretty sure in modern Greek, the letter is pronounced phi. But phi, pi, yeah, I don't know. Let's look at this Cambridge dictionary.
Phi.
Phi.
All right, fine. Why do I think that it's pronounced phi? Vowel in actual Greek would be phi, but English established pronunciation. So I just, okay. All right. Also, thank you for the chat to telling me that it is pronounced phi and not phi, although this is actually a point of contention. I'm sure there'll be a nice thread of the comments about this, but the actual Greek letter, at least in modern Greek, from what I understand, is pronounced phi, but in the US and UK, at least, it's often the mathematical, when referring to the mathematical term, it's the phi. So I'll say phi from now on, so I stop hearing people's pronunciation. And that should also be a const. Now, another thing that is typically done with discrete Fourier transform is to take this sum and then average its contribution over n. So I would also say the real component equals the real component divided by n. The imaginary component is the imaginary component divided by n, so I'm going to add that in. And then someone asked me, well, oh, but this is another question that came in, which was the question, oh, there's I here. Why don't I see I in your formula? In your code? Where is I in your code? And so I isn't explicitly in here, but what I'm doing, I'm referencing I by separating out the real and imaginary components. So the imaginary component is always paired with I, and the real component is in the form A plus BI. So this is A, that's B, but I don't actually have to put I in the equation itself. X can be a constant. Yeah. And the chat is also telling me that x can be a const because I'm not ever going to redeclare that. Now, so let's save this. Let's feel happy that we completed something. I'm going to refresh. I'm going to go back to my code page. I'm going to refresh this, and I'm just going to say, let's make up a variable. Actually, I think I have vowels already. No, it's not defined. Sketch. Oh, y. I called it y. Sorry. Let's make a variable called y, which is here. And now let's say Fourier, DFT, y. And there we go. Something came out. So we're going to just hope that this is right. I mean, I'm not seeing any error. Wait, hold on. N minus 1. Okay, I really shouldn't be looking at the chat. It's making me crazy. Yeah, sometimes I just have to. I'm imagining Simon just wrote, I'm at the dentist. I'm imagining Simon in a dentist chair having his teeth cleaned with like a phone like propped up here watching me live stream, which is totally insane. 11:47. Okay, 40 minutes to finish this. I think we can do it. We've done the hard part actually, sort of. All right, hold on, Matthew. Sorry, I got distracted by the chat. I'm gonna go back to here. All right. So let's just see if that function dft does something and doesn't actually produce an error. So I have the y array, which is my like hard-coded square wave. And if I call dft on y here in the console, we can see I get, right? I had 12 values in my signal. I get 12 complex numbers back, each one with a real and an imaginary component. So this looks good in the sense that there are numbers here. I don't see an error, no red, no not a number. So hopefully we're in the right place. Now, the question is, what do I do with these real and imaginary components? How do those things actually become, how do those things actually become circular epicycles, right? For a circular epicycle, what do I need? I need an amplitude, right? That's basically the radius of that circle. I need a frequency, which is how many cycles through the circle does it rotate per unit of time. And then I also need, this is what's called a phase. And the phase, another way of thinking of it as an offset. So where does the cycle begin? Where does that circular wave pattern begin? That's the phase. So I need these three things. So somehow, what I need to be able to do is I need to be able to say, right here, well, the frequency is something, the amplitude is something, and the phase is something. And the secret to this lies in the fact that a complex number is like a vector. And in fact, here we go. The amplitude is the length of that vector, and the phase is the angle of that vector. Well, so that's amplitude and phase, but what's frequency? Well, guess what? I don't know if there was a clue to this on that Wikipedia page, but the frequency is actually just K. Let's see, frequency, yeah. And discrete frequency components. So the whole point of doing this is to take the signal and divide it into a bunch of discrete frequency components, 0, 1, 2, 3, 4, etc. So here we go. Frequency is K. And that's a little bit redundant, but I might do something with sorting later, so I'm going to need to keep track of that. Amplitude is the square root of the real times real plus imaginary times imaginary. This is basically the magnitude of a vector, the square root of each component squared. This is Pythagorean's theorem at play. And then the phase is that angle, which I can use the A tangent 2, and the y would be the imaginary. I think it's this. I'm going to just reference the code that I wrote before. Yes, I got it right. Okay, so this would be the phase. So now I can say frequency, I can add frequency, amplitude, and phase here. And I can refresh this page. I can say dfty, and let's take a look at any one of these, and we can see, all right, I've got an amplitude, I've got a frequency, I've got a phase. Whew, we are ready. We are ready to start actually now putting this into our code. And the good news is we have the code for drawing these epicycles already. I commented it out. It was right here. So if, in fact, I have this Fourier Y array, I can basically say, hold on, radius, now let's get rid of this n. Let's put, sorry. Let me back up for a second here. I have this code from before that was drawing the results of those epicycles. So I can comment this all back in. But now it's not a specific Fourier series for the square wave. It's whatever's come out of my Fourier transform. And in this case, n is actually It's confusing that I'm using n here, but I'm actually just call this frequency, is Fourier y dot frequency. And the radius is Fourier y times amplitude. And now, not times, is the amplitude. So the frequency is the frequency, the radius is the amplitude, and now I can say multiply time times frequency plus that phase. So, and I know I could get these things out into a variable in like one line, but I'm just going to write this in here, phase. So all the code remains the same. The difference is what I'm going to do. Time is the element that's moving forward, right? It's the angle of, and if the frequency is 1, it takes 1 unit of time for it to rotate a full rotation around. Phase is the offset and radius is the amplitude. So one thing though I have to be very careful about here is that I can't just arbitrarily have this 0.05 thing here. What I need to do is I need to have like the value dt. What is the amount of time I move each frame of animation? This would be 2 pi being a full cycle divided by how many frequency values I have. So now time goes up by this, and we should see now, dare I say, nothing. Hold on. Okay, so that's there. What did I miss? Oh, yeah, frequency times time. Oh. I have a terrible array here. I'm being so silly. Terrible array. Oops, I have a terrible error here. I forgot about index I here. I've got to pull out, right? I'm getting the frequency, amplitude, and phase of each element of the array Fourier y. Oops, sorry about that. There we go. All right, so this looks kind of like maybe it's right, but it doesn't look right at all. Like something's happening that's pretty decent, but it's wrong. So here's the one thing that's a little bit unfortunate. I'm off by 90 degrees here, I'm pretty sure. So let's just add half pi in here because, and there we go. Now, this is actually correct. There's my square wave. Right? I don't have it on its side because I'm doing the y values. This is sort of crazy though, because it's kind of like, is this really what we're doing? The thing is, I have so few values, so it would make more sense for me to actually pre-compute some kind of more interesting signal. So let's forget about hard coding the signal for a second, and let's just say I'm going to have a signal with 100 values, and let's just make them all random numbers. This is going to be a little bit insane, probably, but let's pick a number between -100 and 100. So you can see, look at this. There it is. This is the crazy set of epicycles to draw these random numbers. Let's use Perlin noise. And actually, let's actually create a perfect sine wave. That'll be interesting. And of like some arbitrarily perfect. This is really insane. Whoops. Float. So look at this. I did a Fourier transform, discrete Fourier transform, to have two circles rotating around each other to recreate a perfect sine wave. I could also now do, I could do Perlin noise instead. And like just have it increase by some arbitrary amount. And we can see, let's actually make it much taller. Ooh, why is this not? Okay, wait, minus 250. All right, so there we go. I'm kind of doing nonsense here. But the point is, any arbitrary signal that I have, I can now compute the Fourier. And you can see, by the way, this is it like cycling back to the beginning. That's why it almost looks like this like crazy heartbeat. There's this extra bit here of it, like the first one not rotating at all, just with this offset up, because the values itself don't perfectly average around 0. But this is not the point. This is not the point of what I want to do. The point of what I want to do, and let me just show you to be clear. Like if I just made this like I, like a linear function, you can see this. Look at this. These are all the epicycles. For basically now I've got the triangle wave because it's going down and then back up at the top and down, repeating over and over again. Okay, we are getting somewhere. Now what we need to do is add x's. We need to add x's. So let's have an array of x's. Let's also have the Fourier transform of the x's, and we need to initialize them somehow. We're getting somewhere. Here's the thing. Now this, I'm going to need to do this twice. So this, all of this I should, it's time. I'm going to refactor this now. I'm going to take all of this, and I'm going to write a function called draw Fourier with some arbitrary Fourier. And so this is no longer Fourier y. And so I'm going to leave all of this. And so I can do this twice because I want to say draw Fourier x, draw Fourier y. And actually, I don't want any of this in here. This is going to be here. Hold on. Sawtooth wave, thank you. Hold on. I started going off on, let me back up for a second, because I started just like losing myself in like implementing this without actually like explaining what I'm doing. Let me just go back. Just give me a second here. Let me end. Yeah, this should be x. Thank you. I don't know why, but I just sort of like lost myself for a second. I need to just like take a breather and move on. Because I also want to correct the fact that this is a sawtooth wave, not a triangle wave. Yeah, Chris is saying the half pi offset. I'm going to fix that. And I'm going to sort the circles with their radii. Yes. I'm going to do all of that. Don't worry. Okay. Whew. Okay. Just need a break for a second here. It's noon. I don't know if anyone has a guess. Like, I mean, if you had to guess, taking out all of the wasted time, if this were edited, how much time do you think this video would be so far? Hey, okay, so this, by the way, is not a coffee company that was mentioned in the chat, not to be named, because I'm not buzz marketing it for no fee. But anyway, it does have green on it. 2 minutes, okay. I'm sorry, I just need like a breather for a second. This is where I would be doing 1 hour. It would be less than 55 minutes, okay? All right, I'm gonna Mathieu, you know what would be fun? So maybe this can all be in one video. But if we break it into parts, maybe what I could do is actually record some intros and outros from LA at Processing Community Day. Anyway, but yeah, about an hour, probably. Okay, all right, let me move on. Okay, people are saying 20. There's no way it's 20 minutes, but okay. Okay, deep breath. First thing is, in my excitement and exuberance over what I've accomplished, I was calling this a triangle wave. You know, there's kind of a triangle there. This is a sawtooth wave, which is what I've recreated right here. But I need to take a breath here and talk about what the next step is going to be. The idea now is what I want to do is I want to be able to draw an arbitrary path, which in addition to having y's, I want to have x's as well. So I need to do the Fourier transform twice. Now ultimately, there's another way of doing this where I do one Fourier transform on a set of complex numbers where the real and imaginary components are the x's and the y's. But I'm going to stick into this sort of like simple place that I am right now. And I am going to add two signals now, an x and a y. So I need the transform for both the x and the y. I'm just going to in a sort of silly way, have the x's and the y's be the same. And then I'm going to apply the same exact Fourier transform to both the x's and the y's. And now here's the complicated part. This loop here is visualizing the results of the Fourier transform as a sequence of rotating circles, epicycles. So what I want to do, though, is I think what's going to be good is to refactor this, not later, but now, and put this in a function. Let's call it epicycle. So the idea is that maybe I would get an x and a y. Like that's where it's going to start. And then I get the set of epicycles, and I draw them all. So this is a generic Fourier one. So in other words, the idea being that I could say, and I'm going to get rid of this translate, and I'm going to say basically what I want to be able to say is like draw, what did I call it? Draw Fourier? No, I called it epicycles. Epicycles. Like 100, comma, what's the size of this window? Like 200 Fourier x, and then epicycles, 300, 200 Fourier y. So we should see both of these now. Let's take a look. Epicycles is not defined. Oh, I don't know why I did this capital C. That's probably unnecessary. Okay, great. So we can see, look, so those are, and now the epicycles are the same because they have the same values. Let's give them different values. So let's do something kind of goofy. Let's make it draw a circle. So this is going to be 100 times cosine of, this is so silly, of an angle, and that angle is map I, which goes from 0 to 100 to 0 to pi. This is just so I can have some kind of path to work with. That's like very recognizable, so I know whether it's working or not. And then y will be the sine of that. So we can see, okay, this looks promising, right? Now we can see here are the epicycle calculations for the x's and the y's. Now one thing that's off though is that, remember how I had to I kind of glossed over this, but I was had the thing on its side. This half pi is really like the rotation of the whole thing of how I want to display it. So let's make that an argument here, and we'll call that rotation. And so the y's, oh, that's when I, do I want to, yeah, I think I could just do that when I draw it. That's fine. Where is this now? The y's should be off by half pi, and the x's should not be. And so now look at this. Okay, so in theory now, we're getting somewhere, don't worry. What I want to do, let's position this like over here, and then let's position this like a little bit further over and here, right? And now what I want to do is over there where that mouse pointer is, I want to take the y from here and take the x from there and draw the path. So instead of wave, I was drawing a wave pattern. I now want an array that is the full path. I want to basically get the end result. So let's have this epicycles function return. It should return a value which is a vector, create vector with x and y. So whatever the end result, like the last x and y point, the end of that epicycle sequence. And then, so I have Vx is this, that's the vector for the x's, and Vy is that. And now I want to say path dot unshift. Okay, so I want to create a new vector. This is like where I want to draw the thing. I need a vector which is the x component of Vx and the y component of Vy. And then I want to put that in the path. And then this, let's get rid of this line for a second. I'm going to, instead of drawing this wave, I'm going to iterate over the path. I don't know if I've, this is a little bit of a strange refactoring of what I had before, but I think it's going to make sense to you in a second. Let's see. I might have to come back and explain this. Let's put this in here. And wave is not defined because it is path, path. I'm not going to worry about this right now. Let's take that out. Oh, yeah, it's over there. Oh, it's in the wrong spot. But it is right. So why is it up here? Because, I wanted to sort of like appear, because these are at, I know it. I'm not using the offset. So actually what I want to return is also x plus the original offset. So let's call this offset x, offset y. Oh no, and then hold on. I'm going to figure this out. This is so, what I'm doing now has nothing to do with Fourier transforms. It's just figuring out how the weird way that I want to visualize this, which, now that this video is, I'm going to just say the offset x, I'm going to just save these values because I think what I want is, no, but it should be offset by it already. Hold on. Hold on. I'm just thinking for a second. Why is this not doing what I think it's going to do? This should definitely be multi-part, but I'm... just like... Okay, so that's... Yeah, that's the... Oh, that is right. It's just like... over... I guess I need a whole other offset. Because everything, this is relative to the center. Why would it know where I want to put it? Like I want the, or maybe I have, this is, oh, these are wrong. This x should be up here. Oh, this is like wrong. Vx comma y and Vy comma x. Yeah. They're in the wrong place. Swap them. Yeah. Hold on. Let me go back. Back up. Yeah, they're totally in, they're just in the wrong place. I'm just being totally ridiculous. I have it right. Let's get rid of this offset thing. Sorry, Mattia, this is going to be an edit to go like kind of way back. Not way back, but a little bit back to where I had this. Okay, so this is actually correct. I just put the, now I'm realizing this is correct. I just put these in weird places. Like I want the one that's doing the y over here, the one that's doing the x over there. I don't know why, just like intuitively didn't put them in the right place. So this should be 400, comma 50, and this should be like 50, comma 200. This has nothing to do with Fourier transforms. It's just the weird way. There we go. So I wanted to see them like this. So now you can see those are the Fourier transforms for this particular circle. And let's add a line back in now, which is basically this thing. So I also want to draw a line from vx dot vy, so vx dot x, vx dot y, to v dot x, v dot y. Like I just want to draw these two lines, and then the same thing from vy dot x and vy dot y. Wow, my naming is wildly confusing here. So this could definitely use for some refactoring, but there we go. Now we can see those lines. So this is good. Now I don't like the way this is spaced out. So let's, one way to fix that would just be to make this thing smaller. And that sort of helps me a little bit. But this can move over. I don't know why I put it all the way over there. Let's move this over to 300. Okay, this is a little bit better. Now, let's make something more interesting here, which is, let's start using Perlin noise again. So I'm going to say noise, and noise plus some arbitrary amount. And we can see, look at this. So you can see that this works, and let's give it, let's make the amplitude bigger, and let's give it like 500 values. Oops. And there's also no reason why. This is very silly. These should just be in one loop. But let's give it more values, and let's just say, I divided by 50. I'm just doing like arbitrary stuff, because the whole point of this is to do a drawing. All right. But we can see how this now will take any arbitrary signal and compute the Fourier transform for the x's and y's and draw that path. Now, the nice thing about this is I'm about to almost instantaneously do something to make this much more interesting. I am going to go and grab the coding train logo path. Because the whole point of this is forget about computing a path. The whole point of this is forget about computing a path. I want to have a known path, a drawing. So what I'm going to do is, hold on, edit point for a second. Let me grab this. Call this codingtrain.js. And I'm going to add that in here. Okay. Okay. I am back, and I have brought in a JavaScript file that just has a big array of x's and y's, all in a variable called drawing, which is the continuous path of the coding train logo. Thank you to, I will link to Tom Fevrier on Twitter for sending me this particular path. So what I'm going to do now is if I go to the code, we've done all of this work for this moment. Oh boy, this better work. I'm so excited. I'm going to go here, right? And now I'm going to say I mean, this is a little bit silly the way I'm doing this. Drawing.length, I plus plus. I'm going to go through, right? Remember, this variable, drawing, is just an array of x's and y's. And I'm going to make the x's drawing index I dot x, and the y's drawing index I dot y. Now here's the thing. I happen to know that the complexity of that drawing is way more detailed than I need, and it's going to run very, very slow. So I'm actually going to add a variable called skip, and I'm going to like skip every 10, and I'm going to say plus equals skip, and then I'm going to change this to push. So I'm going to skip and only do every 5 vertices of the drawing. I'm doing this in advance because I already know looking at that, I don't need that many points. So this should now give me all of the points, all of the x's and y's from that particular drawing. And I'm about to go hit refresh and hope that this works. There it is. So there it is. Now, this doesn't look as beautiful as it possibly could. And there's a couple reasons for that. Right now, one thing is, this look like these weird like alien creatures, by the way. But it would be really nice to have the epicycles rendered in order of amplitude. So right now they're rendering in order of frequency, and it's like this strange machine, almost like drawing machine. And it would be amazing to like if someone could build this physically. But what I'm going to do is sort them. So what I'm going to say Fourier x dot sort and Fourier y dot sort. Now, with the JavaScript sort function allows you to pass in a callback, which is essentially a function that tells you how to compare each element, and I want to compare them by amplitude. So I can actually say any 2 arbitrary elements, and I'm going to use ES6 syntax for this. This is a way of, if you haven't watched my arrow syntax and our higher order array videos, this is something would give you background for this. And then I can just say, I think A dot amplitude minus B dot amplitude, right? Because if I get a positive number, it'll put one in front of the other. If I get a negative number, it'll put the other one. If they're equal, it will leave them. So this is sorting each one of those by amplitude. And if I refresh this, oops, sorry, the smallest one is, I sorted it in reverse order. So let's put B here, A here. And let's also give myself, let's clean up some stuff here. Let's make this 800 by 600. Let's set the offsets to width divided by 2, 100, height divided by 2, 100, height divided by 2. Let's set these offsets a little bit more. Let's refresh. Let's shrink this up. And let's move this down a little bit. Plus 100, and let's move this over plus 100, just to give me more room. Will this work? All right. This is the thing, finished. 72 hours later, there it is. Oh, it's off the bottom. Oh no, it's kind of sitting right there perfectly. How did my math, that is totally accidental, by the way. Oh, now it's just going to draw it again over and over again. So no skip. People want me to like get rid of the skip. So I could get rid of it. Let's play with that skip now. But I want to do a couple other things. One thing I want to do is, if time does a full cycle, then I want to set time back equal to 0 and path, clear the path. So let's do that. So let me just make sure once it gets through the full cycle, what's the actual, yeah, there we go. Once it gets through the full cycle, let's make sure it clears it. There we go. Okay, so that's working. I'm like obsessively feel the need to, actually I'm not gonna, I want to like constantly tweak the alphas and the stroke weights, and I'm gonna let people make more beautiful versions of this, and I'm not gonna do that, but people do want to see how this changes with the skip. So I am going to, let me just make the skip 5 or 4. Like I'm gonna reduce it, and let's just see what happens here. So So, and you can zoom all the way in here, and we can sort of see I've got many, many more epicycles. And you can see that it's doing it without the skip. If I get rid of the skip completely or set it to 1, I'm already, like, you can see it's just running way too slow to reasonably, I mean, it's just like got too many things to draw, and so many of these are probably of radius like less than 1. I could probably like eliminate anything that's so small and get it to run faster, but I think I'm going to go with a skip of 8 and leave this be. All right, this concludes this particular coding challenge where I took a discrete Fourier transform, this particular math function, I applied it to an arbitrary signal, 2 signals of x's and y's. Then I rendered those as rotating epicycles and had to draw the path. Whew, I'm very excited that I accomplished this. So there are 2 things that I want to do, probably more than 2, and those are going to come in separate videos if you made it through this one. I am going to first, I'm going to take a break. I'm going to come back and I'm going to make it so that the user draws something and then it computes the Fourier transform. That really, by the way, you should go do that yourself right now. So take this code that I've released, find the link in the video description, and go make a version where the user draws something and then do the Fourier transform. That's a fun exercise. I'm going to do that in the next video. And then I am going to rewrite this so that I have the Fourier transform done with the x and y's together as a complex number, and I just have one set of epicycles rendering the full path. But I kind of like these 2 like x and y machine things. It's kind of cool. Whew. Oh yes, and Melvin in the chat is saying, oh, you could use the quick draw data set. So I'm going to leave that to you, the viewer. Please make this, share it widely, make a version of this that renders random drawings from the quick draw data set. That would be super fun. I would love to see that, okay? If you make any of these exciting, fun, beautiful, strange, ugly, whatever they are, variations on this particular coding challenge, please go to the link to thecodingtrain.com, look for the instructions of how to submit your variation and submit yours. And if you have trouble doing that, file a GitHub issue or something saying, I want to submit mine, but I don't know how, and we will help. Okay? Goodbye, everybody. And I will leave you with something that really needs to happen to this code.
I will refactor this later, you know. I will refactor this later. I will refactor this later, you know.
Okay. Where are we time-wise? 12:30. Okay, I can do a bonus here. The final video would be less than an hour and 20 minutes. All right. So off the top of my head, this definitely needs to be broken into multiple parts. One thing that I could do, I have an idea. So one thing would be to go back and redo the beginning of the video. But now, of course, I feel like there's no way I could do that. And that was, oh yeah, that's pretty interesting. Like, actually, I'm curious to see that as well. Like, what if I skip like 50 points? Yeah. But so the thing is, like, there's a different way of doing this where the transform, the number of epicycles, doesn't have to equal the length of the signal. In that case, I could do some interesting variations, but and yeah, modulating the skip over time would be super interesting. There's lots of possibilities there. I'm gonna let you do that. So let me for a second. Okay. Let me think about this. I'm going to take 15 minutes here, and I'm going to record. Will this be, okay, a couple things. Kathrual is asking, skip by like 23 and don't clear the path. Oh, that's interesting. Oh, that's crazy. Yeah, I'm not sure. That's an interesting idea. I'm going to let you all try these things. Okay, so people are giving me excellent suggestions. The point of me doing this is for you now to go and try these ideas. I can't do all of them, and I have to go soon. But I think what I need, this probably has to be a multi-part. So there's a few different ways of doing this. One is I could redo the introduction knowing it's going to be multi-part, and I could kind of explain what I'm doing again. Maybe I'll try do it. Maybe I actually will do that. And then the parts that would make sense to divide it up, I kind of want it to be all one video, though. You kind of need to get to do the... but what I could do is excise out all the time where I implemented this formula and just end with, like, that could be a separate video. That's so weird, though. Because I think it ties together. I don't think... I think maybe I'll have to wait and let Mathieu... maybe I'll have to wait and... Simon telling me you should have mentioned the more famous version of Euler's formula. What's the... I missed that. Maybe I should redo the intro and explain it's going to be multiple parts. Or maybe some really serious editing could get this down to less than an hour. Full screen. I'm lost here as to how to approach this. I'm also like hypnotized by the fact that this is working. The extra math bits in another video. Yeah. All right, let me record some stuff just in case. This is the problem is normally what I would do is I would just let Mathieu look this over, and then tomorrow I would come back in and record some intro outro stuff, but I'm going to LA tomorrow for Processing Community Day. So in order for this to not wait till next week to be published, which actually wouldn't be the end of the world, but I would look to get it out sooner than later. I feel like I need to try to anticipate those things. Also, I could record some intro and outro stuff just like person on the street with my phone, especially in LA. But no one is giving me. So I'm just gonna. All right. Yes, could you reverse it at the end and make it erase it? Okay. All right. Okay. So I have to take matters into my own hands here. I'm waiting for someone in the chat to like just give me the answer of what I should do, which is clearly not going to happen. All right. So option number one. Which is a little behind the scenes here. Might as well do this live. Why not? I don't know what should be behind me, so I'm just going to record myself talking. I think this actually could work. Okay, stop the presses. Hold up, everybody. So the next bit of this video is a long sequence where I go and actually write the discrete Fourier transform algorithm. And ultimately, this coding challenge ended up being super long, like well over an hour. So what I've decided to do is if you're watching this right now, you can go and watch a separate video where I write the DFT function and go through all of the math and steps for that. But if you continue watching now, I'm just going to go from where that function was finished, And I'm going to get the results of that to keep going with this challenge and eventually render that coding train logo path. Okay? So there'll be a weird cut here, but if you want to see that whole part that I've taken out of this video, you can watch that as a separate video linked in this video's description. I don't know if this is going to work, so I'm just recording this as a possibility. Okay, now. And now what I'll do is, I think maybe, I don't know if this is going to work, but we will try it anyway. Whoops, camera went off. Yeah, okay. Hello, this video is a bit of an aside, and it can stand alone if you want to watch it alone, but this is a companion video to my coding challenge, draw a path with Fourier Transform epicycle magic weirdness thing. And in this video, what I'm going to do is take this particular formula from the discrete Fourier Transform Wikipedia page. I have written it, oops, shoot. I'm going to take this formula from the discrete Fourier Transform Wikipedia page. I'm going to take this formula, I'm going to turn it into JavaScript. So that's what this video is going to do. And then at the end of this video, that function is, wait, let me just do this again. I forgot where I was and what I was doing. Okay. Hello, this video is a little bit strange and a little different than what I usually do. This is a companion video that goes along with my recent coding challenge. Transform. Okay, one more try. Everybody should go now. Stop watching. This is me trying to make this all work. But I have another idea. I'm going to do like a second way of editing this together in a second. So it's going to be a while. I'm going to be here for like another 20 minutes doing this weird interstitial nonsense. Hello, welcome. This is a bit of a strange video, a little different than what I usually do on the coding train, but this is a companion video. You could watch it on its own, but the point of this video is to take this equation formula from the discrete Fourier Transform Wikipedia page and write a function in JavaScript that implements this formula. And the reason why I have this as a separate video is I'm going to use this function, which I'm calling DFT, in a coding challenge where I make this crazy drawing machine out of rotating circles and the Fourier Transform algorithm. So that video has a part cut out. When I did this live, all of this happened in sequence, but it became so long, this implementation is in a separate video. This is me spending way too much time trying to explain this. But keep watching if you want to know the details of how I actually wrote that DFT function. Okay, now I'll do something for the end. Probably. All right, thanks for watching this implementation of the discrete Fourier Transform algorithm in JavaScript. If you want to see how I use this function to make exactly this, these rotating circle drawing machine epicycle thing that renders the coding train logo, then you can click over to the coding challenge where I explain a bit more about how this thing works and implement that as well. Okay, thanks for watching. Okay. I don't. Yes. So Kay Weekman, you're saying, have you considered treating the input as a complex number instead of two separate real ones? Yes. The reason why I kind of wanted to do that as a part two, like I was going to do it as like a second part. I don't know why I did it this way. But yes, I mean, ultimately, I thought I mentioned that at the end of the video, but maybe I didn't. Okay. Now, all right, so now this is my second idea for how to, so I am going to I'm going to redo the whole intro thing and reference all of these pages, references. So now I'm going to do a set of intros as if this was a multi-part video. And I think it would make sense for it to be 2 parts. One part where I get all the way through implementing the discrete Fourier transform function, and the second part being doing the visualizing thing. And by the way, another option, Mathieu, is it could just stand alone as what it is. That would also be fine. So I'm going to do, I just feel like I don't want to, there's no good like endpoint to part 1, so there's not really any reason for me to like release them on separate days. Let me just redo the intro in a shorter way. I think I can safely erase this. Okay. 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 I'm gonna make a new intro, explain that this is especially long. I don't know what to do. You know what, Mathieu? Worst case scenario, I'll come back next week. This will just be a while till we release it, which is fine. It's fine. Okay. All right. Hello, welcome to a coding challenge. I actually just finished this coding challenge and I'm coming back to record a little intro to it. And what I made in this coding challenge is a drawing machine. This is, maybe let's call this like a Fourier Transform drawing machine. And there's a few more things I'm going to do with it. There's going to be some follow-up videos. But this very, very long video, if you can stand to watch it, has as part of, at the end, this. This is the end result. I am using an algorithm called Fourier Transform to take an arbitrary signal, in this case a sequence of x's and a sequence of y's, the path of the coding train logo. Thank you to Tom Fevrier. I will link to Tom Fevrier's Twitter, who provided the path for this particular logo, to trace the path of the logo through this sort of sequence of rotating circles, sometimes referred to as like epicycles. Okay, so what's going on here? So this first thing I should mention is this is a continuation of my coding challenge Fourier series. And so what I did in that particular coding challenge, which was inspired by a Smarter Everyday video on the same topic, was create the Fourier series for a square wave. I don't know why I just had to write that. But in this video, I'm going to do something different, which is I'm going to use the Fourier Transform algorithm. And these are different concepts. I somewhat conflated these in my previous video. The idea of the Fourier Transform. Now, where I know this algorithm from, where I learned about this algorithm first in like learning about coding and creative coding and new media and sound and video, is with the terminology FFT. And actually, if you go into the P5 sound library, you'll see there is a class or function called p5.fft. I don't remember exactly what it's called, but something like that. The F here stands for fast. Fast Fourier Transform. The algorithm I'm going to implement, by the way, is discrete Fourier Transform. And so time out for a second. Now this is where I'm going to like optionally say something. But this could also be just cut out. Depending on whether we leave the Fourier Transform thing in or not. Okay. My implementation of the discrete Fourier transform algorithm is actually in a separate video. I'm just going to use the function directly in the code as I do this coding challenge, but you can watch that video as well to see all of the code for that. But now, why is this FFT thing, where is it typically used? Well, it's typically used in signal processing, but a familiar place where you might find that is in audio signal processing. So let's say you have some arbitrary sound wave that maybe looks like this, and it has a really like high-pitched, awful like screeching sound in it. How would you filter that out? Well, if you could take this sound wave pattern and break it into a bunch of smaller sound waves, a bunch of sound waves that have varying amplitudes and frequencies, then you could sort of remove the one that has this sort of like high-pitched sound in it, and then add them all back together and get a new sound wave. So the idea of a Fourier transform, and I think I said this in the Fourier series, it's unsmoothieing a smoothie, right? If we could take a smoothie that's made with like blueberry, mango, and strawberries, and like separate it out and then put it back together without the strawberries, this is essentially what happens in signal processing. But in this video, what I'm going to do is instead of the signal being an audio, it's going to be a series of x values or a series of y values. And eventually, there's actually a way to do that with the x, y values together that I will get to. So I am not going to go too deep into the math in this particular video. I'm not going to derive the Fourier transform algorithm. I'm not going to talk about fast Fourier transform. I'm just going to use a very kind of crude, discrete Fourier transform implementation just to get the thing working. If you want to know more about the math, though, let me reference a few really key references. The 3 blue 1 brown video, but what is the Fourier transform, will give you an infinitely better understanding of what the Fourier transform algorithm is and what it does and even how it works. Way better than my like trying to ramble through that over on the whiteboard. I would also highly recommend this gold-plated goof video, Fourier analysis for the rest of us, which goes through the details of the math in a much deeper way. And then there's this wonderful video from Mythologer, Epicycles, Complex Fourier Series, and Homer Simpson's Orbit, which will give you the full story of everything that I'm trying to do. But hopefully what's useful to you that's different in my video than from these is I'm just going to sit here and attempt to code the thing. And I know that it's going to work because I already did it. And here is the result. So enjoy. This is a very long video. I hope that if you watch it, you get the code, you make your own variation of it. Please share it with me. You can go to thecodingtrain.com to the particular coding challenge page, and there's instructions on how to submit a user community variation thingy there. Okay, goodbye. Enjoy, or not, or whatever. All right, so I don't know. I don't know if that's good. Oh, yeah. Was that? I don't know if that was better. I don't know if that was better than my first try. And I also didn't say, I could do one more. No, I just don't think it should be multi-part. Okay. So, I don't know. I don't know what to do about this. Okay. In an ideal world, the whole thing would just be one video. Okay. It is multi-part because now I'm going to do something else. Okay. Oops. All right, I'm going to do one more. I have to go soon, but I'm going to do one more thing. So let me actually want to save this as its own thing. So hold on. Bear with me for a second. I'm going to call this Fourier coding train. Oh, actually, no, hold on. And and then user drawing. Take, okay, and so sorry, my brain is broken. Okay. Sorry. Oh, okay, I know. There we go. User drawing. Okay. And I mean, maybe I should do the well, whatever. Sorry, I'm just like lost my mind here. Okay, there we go. Okay, Simon wants me to say Euler's formula and also say that e to the I pi plus 1 equals 0 is the more famous version of the formula. Okay, I've said it. Okay, let's close all this. Let's open this up. Okay. Okay. All right. Here we go. Last bit for today. So Keshav is asking, when does the edited video go up? So the edited video would normally I do stuff on a Friday, and then the edited video goes up Monday or Tuesday. Because today is Wednesday, in theory, it's possible the edited video would be later this week, but more likely next Monday or Tuesday or sometime over the weekend. There's also the added complication that I am going to LA for Processing Community Day tomorrow, and it might actually make the most sense for me to come back and record the explanation and stuff later after the fact again, in which case the edited video would be later next week. So all of these things are possible. Okay, and I almost want to do the thing where I change this to a complex number input. I can't do that right now. I can't. I have to go. I'm going to just do, all right. Hello. All right, this Fourier transform stuff is so fun and interesting and weird. This is the end result of the the very long coding challenge that I just completed, and I'm going to be doing a couple different follow-ups. So this first follow-up, I just want to write the code to, instead of using the coding train logo, have the user draw a path, and then have Fourier transform that and render it. The second follow-up that I want to do is, instead of having two separate rotating sets of epicycles, one for the x's and one for the y's, I can actually treat the input to the Fourier transform as a complex number itself and have one set of epicycles. So I'll come back and do that in a separate video that'll come out later. You could try that on your own, but I will get to that. So in this video, I'm just going to see, because I just really want to see it, if I draw a path, I want to Fourier transform that. So how am I going to do that? So the thing that I need is, well, one thing is I no longer need this codingtrain.js file, which has the full path of that particular drawing. Instead, what I need is I need a variable called drawing, and I need probably a state. And I'm going to say something like user, these will be the two states of the program. So in other words, whoa, if the state, so I'm making two constants 1 is a 0, 1 is a 1, and I know I could use like enumerables or something like that, but that's not me. You know me. I can't be bothered. I'll refactor this later. I won't play the song. So I'm going to start with the state being user. And if the state is user, if state equals user, I'm going to do something different than if the state is Fourier. And there's only 2 possibilities here, so I could use a Boolean, but there might be other things I want to do with this later. So let's just start with that. And there's no reason for me to do the Fourier, any of this stuff in setup anymore. But I do want to have this code for reference. And then I think what I want to do is, when the mouse is pressed, well, the state should be user. And if the mouse is, when the mouse is released, these are 2 global event functions. I want to make the state Fourier. So basically the idea is when I click the mouse, I'm about to do a drawing, and I need to record all of the points. So in draw, if the state is user, I want to say the current point is create a vector, which is mouse x, mouse y, and then I want to add that to the drawing. And what I would do is always when I press the mouse, reset the drawing array to an empty array. And then when I release the mouse, I would calculate the Fourier transform. And I'm going to assume that I can use a skip of 1. And this should work. I mean, my offsets are going to be wrong, but let's see what happens. So, so now, if I go here and I hit refresh, there's nothing. Now, in theory, if I were to draw a circle like this and release, there we go. There's my drawing. Now, it's weirdly down here in a different place than I drew it, and I wasn't able to see it while I was drawing. So I need to fix that a little bit. So one thing that I should do is, and please let me just minimize this because it keeps coming up. One thing that I should do is probably record the points relative to the center of the window. And then also, I also want to be rendering it. So I would want to say for every point, actually, I'm going to say every vector in drawing. Let's actually render it while I'm drawing it. Begin shape, end shape, stroke, and let V of drawing, stroke 255, no fill, and just set a vertex to, this would be like the shortest video ever compared to the last one, instead of vertex. So this is me like when the state is in the user drawing state, I'm going to render all the vertices. And there's going to be a little bit of a problem with this. Ooh, oh, but only, so state actually at the beginning should be, I just realized, the state should be -1, right? I'm not going to, the state is something else. It's like the start, and I probably should have some instructions like draw something. So the state is -1 because I actually don't, and then when I click the mouse, but you see my drawing is up there, but this worked. Okay, great. So now what I want to do is, if I think about this correctly, I just need to, I'm storing the points relative to the center. I could use translate or something smarter here, but I can just set them when I draw them relative to the center. So now, here I am. I'm going to draw a very elaborate like figure 8 pattern like this. And then you can see now there it is. And it's a little bit off, right? It's not, it might not be exactly where I drew it, but you can see now. And then if I can draw a circle. Oh, okay, didn't recalculate the Fourier transform. Oh, it just added it to the end. How weird. I thought I when I do mouse released, I should redo the drawing. Why didn't this work? Right? If I do one thing and then do another thing, why is it still both? Because when I click the mouse again, it should reset the drawing to 0. Oh, the X's and Y's didn't get reset. Because I have this weird extra, okay, so that needs to happen. Okay, so now if I draw this circle, I get this, and its offset is wrong. And then if I do this, it'll do epicycles for that. Okay, so let's get the offset stuff actually correct. And so one way to do that would be to actually just here have everything be relative to the center. So where do I calculate the Fourier? Where do I draw the Fourier stuff? Here. Let's get rid of this plus 100. Okay, so now, if I draw very slowly this circle right here, as soon as I let go, we're going to see it draw it right there. There we go. So this coding challenge is now complete. Let's just make sure I'm going to draw like now this very, like my drawn version of a sine wave. And there we go. Now my drawing machine is rendering it. Okay, so I just wanted to do this to show you at least some creative possibilities here. There's so many things that could be done to refactor this, to make it better. But I just wanted to do this follow-up because this might help you start to think of other creative ideas of things you might be able to do with this particular Fourier Transform epicycle drawing coding challenge thing. Now, I am going to return at some point in the future and do one more video where instead of doing the X's and Y's separately, I process them together. And that I think will also be something fun and interesting to play around with. So it will need a little bit more sense of how complex numbers work in order to do that. But so you might want to go, if you haven't watched, go back and make sure you review the implementation of the discrete Fourier transform algorithm, because I'm going to basically be redoing that, but have the inputs be complex numbers themselves. Okay, thank you very much. See you in the future. Please share with me versions of this that you make, and I will see you soon. Goodbye. Okay. Oh, interesting. You can reset an array using splice 0, which lets it be a const if you wish. Great. Okay. I'm going to draw. It has to be a continuous path. This is way too much fun. I'm definitely going to have to screen capture this. Hold on. So I'm going to use this. Ah! I lost it. I have to do it again. Okay. I could do this on my own time. Wait, hold on. Oh, because the stupid mouse, if I click anywhere. Oh, wait, I'm not screen capturing. I will, hold on. Will this, let's record it like this. A little behind the scenes here. Let's make a nice little recording of this. Okay. Can I get this in 30 seconds? I think that's the limit of Giphy's recording. I have to do it in 15 seconds. Whoa, what just happened there? What is going on? I broke something insanely. What the? There's a bug in my code. Wait. All right, I'm gonna make a, but why? I feel like there's, oh, weird. There's just like something left over. See what's going on. Shiftman, see my concept above. You also need to reset the phase of the epicycles. Ah, thank you. Thank you. All right, so that's a bug. I don't think I'm gonna. Also, okay, quick little interstitial. I also need to make sure I reset time back to 0. I forgot about that before. I don't know if that's, let's. Oh, weird. No, I still, it's not just resetting time. Drawing X, Y. Right, like. What is going on? Oh, do I need to reset this all in released? Shouldn't matter, right? I mean, yeah. Oh, path. Oh, there's too many things to reset. I forgot about path. That's the problem. Yeah, okay, I'm just being silly. Okay, hold on. Okay. Yeah. Okay. Oops, this is a weird edit point in this video because when I made it, I actually forgot to reset a bunch of other things. So really for this to work well, even though as the video goes on, it kind of works anyway, I should be resetting time back to 0 because I want to start at the beginning, as well as path, as well as resetting the path as well. Sorry, these don't have to be reset. Ugh. One more time. Because Fourier X and Fourier Y will get those get created as blank arrays. So those actually don't have to be reset. Sorry for this weird edit point. I'm jumping in because when I did this coding challenge just a moment ago, I forgot that I also need to reset, in addition to resetting the drawing and the X's and the Y's, I also need to reset the time back to 0. So it starts at the beginning, and I better like clear out that path. So this is pretty awkward. There's probably a nice way to refactor the resetting of everything, but this will make it work with fewer bugs. So thanks, and now the challenge is going to continue. So let me make sure that gets this. And there we go. Okay, so now just humor me for a second. I really want to. Oops. Oh wait, I'm not capturing the capture cursor, yes. Okay, there. Now I have my GIF and starts right about here where I draw it. And then it Fourier transforms it. Did it not start at the beginning? Who knows? No, it did. And then, this I should be doing on my own time, not while I'm live streaming, by the way. There we go. Let's make this 640. And save as on the desktop. I'm going to make oh, sure, make it a large GIF. I don't care. Looks like it grew. Okay. Geez. I wanted to make it a GIF so that it, but I have a feeling this is just going to be, oh no, it's only 2.2 megabytes. That's totally fine. Give me a break. Give me a break, Giphy recorder who seemed to think that, right? Am I crazy? Yeah, 2.2 megabytes, that's not too big. In fact, I can make the frame rate high. Save as GIF. Okay, all right, apologies everybody. I'm done for today. I am going to go. So another thing that you could try, by the way, is could you come up with a way to not have to, ooh, I should mention that, to not have to do it as a continuous path? That would be kind of interesting, right? How could you make multiple sequences that draw break the path into parts, and actually know which parts are lifted up and lifted down? That would be interesting. Okay, so I will be posting all of this code and everything soon. The next live stream, let me just see how this, wow, it takes quite a while to start. 4.2 megabytes, all right, I'll deal with this later. All right, I have to go. Thank you everybody. This has been a almost 3-hour live stream, not 3 hours. I feel satisfied that I made it through this project. The code will be posted and out there soon enough, but you might have to wait even a whole week for the edited version of this video to come out. But I will be back the next live stream, and I don't know what I'm going to do yet. The next live stream will be a week from this Friday. If you will be in Los Angeles and I see you at Protestant Community Day, please let me know. And then I also just want to remind you that I am making plans for a new playlist of videos related to working with data and APIs. And so if you have ideas for how I should structure this and examples you'd like to see me to do, how to sequence it, this will be a new set of tutorials related to a class that I'm teaching. And so feel free to file issues with questions or ideas or even pull requests if you want to help me collaborate on the code examples and the syllabus outline. Okay, so DT6 asks, when are you going to post the code? I will do that by the end of today. Actually, yes. So I will do that by the end of today. Just tweet at me if I haven't done it, and that will remind me at Schiffman. If, by the way, you can actually find it. It's not the code that I wrote today, but basically pretty much the same code is here at github.com/Schiffman4a-drawings. This was my practice for it. All right. Thank you, everyone. Close attitude. I'll sit here. Oh, wait. Simon, you can help me out with your perfect pitch here. Why is this all buzzy? What's buzzing? Is it the tuner? No. There's something rattling. Do you hear that? What's rattling? That rattles. Even more? Even more? No rattle. Is there something in there? Oh, my sad ukulele. Something like, but it's just been sitting here all this time. Somebody came in and sabotaged me. This is such a nice ukulele. Yeah, I hear something. Oh well, I think maybe now is not the time for me to figure this out. I hear something shaking. Is it? What's loose? Is it something inside there? Let me take off the strap for a second, because that's... Make sure it's not the strap. No? It's fret buzz, yes. I think. But I hear something shaking. Could there be a crack? When FR3 Foo, when is the edited video with MPJ Fun function coming out? I don't think there's any edited video. I don't know what that's referring to. The MPJ live stream, I don't think has an edited component. It's definitely something up top here that's rattling. Or not. All right, I will deal with this later. Yeah. Is there a crack? That's weird. Strap screw or neck adjustment screw inside the cavity. It sounds like it's up here. Although not necessarily. Oh, you know what it is? I have no idea, because it resonates all around. So it sounds like the tuning pegs. Okay, Jay-Weez is the tuning pegs. I am a ukulele player. So if it's the tuning pegs, yeah, it's buzzing up here. Look at this. If I pulled my thumb on here and it goes away. So I think it's just this one is probably loose. I probably just need to tighten this screw, right? It's probably this one that's rattling. Yeah, tuning pegs get loose. That's what it is, because if I hold my... Well... Well, I'm going to put this aside, and I will come back to that another time. The next time I need that is for the next year's holiday fundraising. Okay, goodbye, everybody. I will be posting the code soon. Thank you for joining me on the coding train today. It is 1:15. I'm going to go. I will be in Los Angeles at Processing Community Day. Please say hello if you are there. I will be back in live streaming a week from Friday. Stay tuned for more ML5 tutorials, nature of code stuff, some coding challenges, but in particular, a new set of tutorials about working with data and APIs in JavaScript. Mwah! And I will refactor the ukulele later. I'm going to be clicking this stop live streaming button in a second, if I could find it. Oh, let me see here. Thank you, by the way, to Alizm for the super chat and Subha Parikh for being a new member. I now, by the way, figured out a way to have a running log of any super chats or new members that I can refer back to later during the live stream. So if you posted one, I will see it and be able to answer the question. But there is just a couple here. Thank you very much. Oops, and now it just logged me out of something. That was weird. And now I'm going to hit stop live streaming. Where is that stop streaming? There it is. Goodbye.